Okay, we're starting Module 4, and this module is all about linear equations, and we'll be here for quite a while. There's many lessons. We'll be here for several weeks in Module 4. So Lesson 1 is titled Writing Equations Using Symbols. So this is something that I think many students are already familiar with. So this does move fairly quickly through this. We'll try to take it systematically and try to get some good habits going as we start this module. And this is the meat of the algebra for our year. So so we'd be writing equations using symbols. And so let's look at these two statements. How are these two statements related? So just study them for a minute and we'll go on. Okay, so the one is a lot of words. The number 1157 is the sum of the squares of two consecutive odd integers divided by the difference between the two consecutive odd integers. Okay, so that's a lot of words, whereas down below we've used a variable x to represent a number. In fact, in this example, we would want to say something to the effect of let x be, now there's two odd integers in this problem. Let x be the first odd integer. Okay, now this is a very complicated example that we're not going to solve, and yours won't be quite this complicated, but they'll be very similar to this. So we're going to let x be the first odd integer, and then we can find all the parts of this statement up here in this symbolic language. And symbolic language is really important in mathematics. It was first developed in the 1600s. Prior to that, this would have been the type of thing that mathematicians would have written, and then to solve it, they would be writing words to express their steps in solving it. So this type of symbolic language with an equal sign, operators and things like that, was kind of a revolution in math, and it allowed mathematicians to go much, much further than they could have otherwise. Okay, so we will be practicing putting English phrases into mathematical language in this lesson. Okay, so I wanted to start with a few tips about using symbolic language. You should always start by defining your variable. Oh, whoops, sorry, I'm not very good with this yet. You always want to start by defining your variable, right there. Stating what you want each symbol to represent. So in the previous example, we let x be the first odd integer. So it's an example of what I mean by defining the variable. And we're going to see that over and over again. We're going to use these steps here. So we'll come back to this again, but here's just a few tips. Also, there's not just one correct way to write a mathematical statement. So sometimes they can be represented by more than one correct symbolic statement. So that means that when correcting your work, your homework against an answer key, you're going to have to maybe do a little more. It might not exactly match, but it still could be correct. So that can get a little tricky sometimes, but you'll get good at rearranging these equations that we'll be translating and figuring that out. So just know that there's more than one correct way to do this. And it always helps to break each problem into smaller parts. And sometimes to put simpler numbers in so that you know which operations you might want to be using. Okay, so when we're using symbolic language, we're going to be looking for clue words. And some of the clue words are for operations, like adding, subtracting, multiplying, and dividing. So a clue word for add could be sum. Clue word for subtract could be difference. Okay? Think about others. Taken away from, added to. Multiply could be maybe the word product, because when we multiply two numbers, the answer is called the product. For divide, could be quotient, or how many goes into, or, these types of things. So always looking for words that give clues to operations, because those are symbols that we use to show what mathematical operation needs to be performed. Okay, and then we're going to be working with equations in this lesson and in this module. And so there's equations are two expressions set equal to each other. There's going to be an equal sign. So we want to look for words that signify equality. The most common word for that is. Okay, an example here is the sum of a number and 5 is 6. So the sum, there's our addition word. The sum of a number and 5 is 6. So if I let n be the number, then I can write my statement. The sum of a number and 5, the sum of a number and 5, n plus 5, is equals 6. Okay, so we're looking for those clue words when we're doing these, and that will be really helpful to you. Okay, so here's an example. We're going to do several examples before we get to your classwork page, so you can just follow along. You're going to have plenty of examples in your classwork, so if you want to just listen to these and do them on your paper, but you don't have to completely copy all this down. So just work as we go along. Okay, so example 1a says expressed with symbolic language. A whole number has the property that when half the number is added to 15, we get the number itself. Okay, so a whole number has the property that when half the number is added to 15, we get the number itself. Okay, so we're working with a number here. So we're going to let, whoops, got to get my pen here. Let x be the number. Okay, so we'll let x be our number here. So a whole number has the property that when half the number is added to 15. So let's represent half the number. So to represent half the number, there's a couple ways I could do that. I could say 1/2 times x, 1/2 of x. And remember, when I'm multiplying, I don't have to use the multiplication sign. I just put the coefficient out in front. So this stands for 1/2 of my number. So when half the number, so that's where I am right there, is added to 15. So I want to add it to 15. So I can put the 15 on either side. So half the number, right here, there's half the number, is added to 15. So that'd be 15 plus 1/2 x. Okay, we get the number itself. Okay, so where's my equal sign there? Okay, well, it's we get the number itself. So that means that it's equal to the number itself. Okay, so now I've got my whole statement here, and it is an equation. So I've got when half the number is added to 15, we get the number itself. Okay, let's look at a slightly more complicated version of this same basic structure. Okay, so example 1b says, express with symbolic language. A whole number has the property that when the square of half the number is subtracted from 5 times the number, we get the number itself. Okay, so this one we're definitely going to want to break up into some smaller parts so that we can work with it. So first step we want to do is define the variable. And so why don't you go ahead and do that? What would we write for that step of defining the variable? So pause the video and define your variable here, and then start up again. Okay, so I would just do the same thing. This would be let x be the whole number. Okay, so x is my number, and then I want to start. So try this out. You can try this out on your own. Let's go in here. Has a property that when the square of half the number. So let's see if we can work on just that part. The square of half the number. See if you can represent that part with symbols. Okay, so what I would do is I would have half the number. So one way to do that is 1/2 x. And I want the square of half the number. So I'm going to put all that in parentheses so that I can square it. Okay, so that's one way to do it. You may have come up with a different way to do it. So some that I'm thinking of, you could have, there's half the number squared. Okay, and if I want to, we did this in the first module, if I want to get rid of the parentheses, I could write this as x squared over 2 squared, which would be 4. So all three of those would be representations of the square of half the number. Okay, but I only need one, so let's get rid of a couple of them so we can move on. Okay. All right, so that is going to be subtracted from, let's get another color, is subtracted from 5 times the number. So when the square of half the number is subtracted from 5 times the number, so this expression that we have right here, this thing we wrote, is going to be subtracted from something. So let's go ahead and represent that. So it's going to be subtracted from something, and what it's subtracted from is 5 times the number. Okay, so we have the square of half the number is subtracted from 5 times the number, and when we do that, we get the number itself. Let's pick another color here. So we get the number itself. So there's our equal sign. Another way to say we get the number itself is to say it's equal to the number itself. So 5x minus 1/2 x squared is equal to x. Okay, now notice you're not being asked to tell me what x is. You're just being asked to express this with symbolic language, and you don't actually have the tools yet to really solve an equation like this. Maybe you do, but it's a little bit beyond what most students have had so far. So you're not being asked to tell me what number would work for x here. We're just expressing with symbolic language. Okay, let's look at another example. Okay, here's another example, and we're asked to express with symbolic language. Okay, so Paulo has a certain amount of money. If he spends $6, then he has 1/4 of the original amount left. Okay, so think about what is the first thing that we want to do when we have a situation like this that we need to translate into symbolic language. Okay, so our first step is always going to be to define a variable, or sometimes more than one variable. So we need to think of a symbol and then tell what it's going to represent. So I'd like you to pause the video and do that now, and then restart and see what I've done. Okay, so Paulo has a certain amount of money. Okay, so we don't know how much money he has. So that's a pretty good clue that that's our variable, the certain amount of money. Okay, so we're going to let X represent the amount of money. Okay, so he's got a certain amount of money that he's starting with. We're going to let X represent that amount of money. Okay, so now we need to see what we can do with that, what information we're given and how we can use it. Okay, so we're told that he spends $6. If he spends $6, so how could we represent him spending $6? Well, he had a certain amount of money to start with, and that's our variable X. If he spends $6, think about how you could write that algebraically. Okay, so I would write X minus 6. My original amount of money is X. He spends $6, so then he would have X minus $6. Okay, so let's keep reading. If he spends $6, then he has 1/4 of the original amount left. Okay, so we can express 1/4 of the original amount. Use a different color here. 1/4 of the original amount would be 1/4 times X, or 1/4 of X. Okay, so how can we put those two parts together? Let's read it again. Paulo has a certain amount of money, and we're calling that X. If he spends $6, then he has 1/4 of the original amount left. So what you should be able to see here, or what you may have noticed, is then he has is kind of our equal sign right there. So he spends $6, that's X minus 6. Then that's equal to 1/4 of the original amount left. Okay, so you're going to go through this type of procedure with each of these types of problems. You're just taking it bit by bit and putting it together. Sometimes you might go down the wrong road and have to backtrack a little bit, but notice how I've read this sentence several times in the process of putting it into symbolic language. So that's important to do, because if you have word problems of this type, this is the biggest step. Solving it is the easier thing to do. Translating it is usually the hardest part. And sometimes even just this defining the variables is the hardest part. Okay, let's look at another example. Okay, so this next example is another one we're to express with symbolic language. And it says, when a number is taken away from 57, what remains exceeds 2/3 of 57 by 4. Okay, so once again, we're going to start by defining our variable. So the thing that we don't know, it's not a variable, it's an unknown. When a number is taken away from 57, what remains exceeds 2/3 of 57 by 4. So we have this number that's taken away from 57. So it's going to be our variable. So we're going to let x be the number taken from 57. Okay, so if x is that number taken from 57, pause for a minute and think, how would you represent that with symbols? Just this first part. Okay, so a number, our number x, is taken away from 57. Taken away makes us think of subtraction. So this would be 57 minus x, because the number x is being taken away from the 57. Okay, so we get 57 minus x. Okay, so what remains, and that would be this part, the 57 minus x is the difference. It's what remains after that number is taken away. So what remains exceeds 2/3 of 57 by 4. Okay, so it's going to exceed 2/3 of 57 by 4. All right, so let's work on the 2/3 of 57 first. This is similar to the 1/4 of x, but 2/3 of 57 is a multiplication problem. Of usually refers to multiplication. So this is 2/3 times 57. Okay, so what remains exceeds 2/3 of 57 by 4. So we have to do something with the 4, and we have to think about where our equal sign would go. So you might, we could put it here and then think about what's going on. So when a number is taken away from 57, that's this over here. When a number is taken away from 57, we get this. And what remains, that's this amount after I do the subtraction, exceeds 2/3 of 57, is right here, exceeds it by 4. Okay, so exceeds seems to make us think of addition, because that's what it's greater than something, it exceeds it. So which one of these quantities, is it the 57 minus x or the 2/3 times 57 that's bigger? Something exceeds the other by 4. So let's read it again. When a number is taken away from 57, what remains exceeds 2/3 of 57 by 4. Okay, so what they're saying is that this is bigger. So our plus 4 would go on this side. So we're going to take 2/3 of 57 and add 4 to it. So what remains exceeds 2/3 of 57 by 4. So I add 4 to that, and that gives me that side of the equation. Okay, this is a tricky one. This one's not easy, but you can do it bit by bit. Another way, I want you to look at this representation of it, and let me do it in our same colors. What if I said 57 minus x, and then I subtracted this expression, the 2/3 times 57, and I said that equals 4. Okay, so what is that saying? What is that one saying? Well, let's look at it. It's actually an equivalent equation, so both of these would be right. But what this is saying is it's just interpreting a little bit different. When a number is taken away from 57, that's this part. When a number is taken away from 57, what remains exceeds 2/3 of 57 by 4. So what that means is if I take that remaining amount and I subtract off 2/3 of 57, it should equal 4, because this number here, this part, is 4 bigger than that number. Okay, so what that's saying is that this equation and this equation are equivalent. They're just two different ways of writing the same thing. Okay. Okay, this next example is going to kind of show you how to do something very specific. Okay, so again, we're going to express this statement with symbolic language. The sum, it's addition, right, of 3 consecutive integers is 372. Okay, so we need to know what this word consecutive means. And it will come up in your homework, and it just means basically in a row or in order. Okay, consecutive, next to each other. Okay, so 3 consecutive integers could be like 2, 3, 4, or 71, 72, 73. Could even be, since it's integers, it could even be like -2, -1, 0. So there's lots of ways, but they're in a row. Okay, so let's look at this again. The sum of 3 consecutive integers is 372. Okay, so when you do this, we could have 3 variables. We could have x, y, and z to be our 3 consecutive integers. We could do that, and then we could just say x plus y plus z is 372. We could do that, but if we ever have enough information, that doesn't really use the information that they're consecutive integers. The x, y, and z could be any number. So let's use all the information we have to write a better equation, okay, one with more information in it. So when I do this, I'm going to let x be the first integer in the sequence. Okay. So if x is the first integer in the sequence, what are my consecutive integers? Well, they would be, okay, the first one would be x. So to find the next one, I could just take x and add 1. It would be x plus 1. And then my third integer would be x plus 2. So then no matter what x is, that's all 3 of my integers. If x is 7, then this gives me 7, 8, 9. If x is 0, I get 0, 1, 2. I get my 3 integers. Okay? And it uses all the information. The fewer variables or unknowns that I have, the better. Okay, so the sum of these 3 consecutive integers is 372. So I'm going to add them together. So, whoops. So x plus 1 plus x plus 2 is equal to, there's my is 372. The sum, I'm adding, of 3 consecutive integers is 372. Okay, so that's a pretty cool way to do that. We will be rewriting these types of equations in the next few lessons, but you might notice that you could rewrite this as 3x plus 3 is equal to 372. And some of you might have enough experience with this that you're doing that already, and that's great. So either of those, that's an example of two different statements that would represent the same that same sentence or that same relationship. Okay, moving along. All right, this one's similar, but how would we represent the sum of three consecutive odd integers? Okay, well, whoops. Okay, so we want to let x be the first integer in the series. Okay, so, well, and actually, let's be more specific. It's going to be odd. We're going to let x be the first odd integer. Okay, so x is the first odd integer. So let's think about this. If I have an odd integer, the next consecutive odd integer would be 5, and then I could have 7, 9, and so forth. So in order to get from one odd integer to the next, this time I'm not adding 1, but I have to add 2. So the sum of three consecutive odd integers would be x. Okay, so there's my first odd integer. My next odd integer would be x plus 2. And then the third one would be x plus 2 or x plus 4. And the sum of those three is 93. So equals 93. Okay, and I can, because this is all addition, I can rearrange things. So this is x plus x plus x plus 2 plus 4 is equal to 93. There's a different way that could be represented. This one looks like 3x plus 6 is equal to 93. So all of these are equivalent ways of representing that statement above, and any of them would be correct representations of it. Okay. Okay, now we're ready for your classwork page in your notes. You have exercises 1 through 5, and if you're feeling ready, just go ahead and work on all of those, and then come back and check. If you think you're struggling, you just go ahead and check each problem one by one, playing the video along. So go ahead and pause now, and then come back, and I'll work out these problems one by one with you. Okay, so let's go over number 1 together. It says the sum of 4 consecutive even integers is negative 28. So again, following the model in those examples, let's let x be the first even integer in our series. And to get from one even integer to the next, we'll be adding 2. So the first even integer is x. The second is x plus 2. The third is x plus 4. And the fourth is x plus 6. And if I add those all together, you see the addition signs in between each one of those. If I add those all together, I get negative 28. All right. Okay, so for number 2, we can let n be the number, or x or y or whatever you want to call it, the number that's talked about in this, because it says a number is 4 times larger than the square of half the number. Okay, so the square of half the number is this part right here. So half the number, n over 2, n divided by 2, or you might have written 1/2 n. And then it says the square of 1/2 the number. So I have to take the whole n over 2 and square it right here. Okay, so a number is 4 times larger than the square of half the number. So if something is 4 times larger, that means I'm multiplying it by 4. So my number, n, equals 4 times the square of half the number. So that's my representation right there, symbolically. Okay, pause and do the next one. Okay, here's the results for number 3, which says Stephen has some money. If he spends $9, then he will have 3/5 of the money he started with. Okay, so Stephen started with a certain amount of money, and that's what we don't know, and so that's our unknown. So let's let X be the amount of money Stephen started with. Okay, remember, you're always writing this defining of the variable statement because it makes the rest of it make sense. Otherwise, we don't know what it is. Okay, so he started with some money. He spent $9. So how can I represent that? Well, it would be X minus 9. He spent $9. He has $9 less. If he spends $9, then he will have, there's our equal sign. He will have 3/5 of the money he started with. So 3/5 of is 3/5 times the amount of money he started with is X. So 3/5 of X, or 3/5 times X. So X minus 9 equals 3/5 X. Okay, number 4. Okay, so number 4 says the sum of a number squared and 3 less than twice the number is 129. Okay, so we have a number. That's our unknown. So we're going to let n be the number. And so the sum of a number, so here's sum, there's our sum, addition. The sum of a number squared and 3 less than twice the number. So I have the sum of something. There's 2 things that I'm adding. The 2 things are a number squared and 3 less than twice the number. Okay, so here is a number squared. Here is 3 less than twice the number, 2 times n minus 3. I'm adding those 2 things together, and the statement says the sum of a number squared and 3 less than twice the number is, there's my equals, is 129. Okay, now if you rearranged any of that, but it's equivalent to this, then that's fine. Okay, we're going to pause and do 5. Okay, so let's read it. Miriam read a book with an unknown number of pages. The first week, she read 5 less than 1/3 of the pages. The second week, she read 171 more pages and finished the book. Write an equation that represents the total number of pages in the book. Okay, well, if we let X be the number of pages in the book, since that is our unknown, then we can represent what she read the first week by this first part of the statement. So let me grab a different color here. So 5 less than 1/3 of the pages. So that would be this right here. 1/3 of the pages would be 1/3 X. 5 less than 1/3 of the pages would be 1/3 X minus 5. So that's the number of pages that she read the first week. The second week, she read 171 additional pages and finished the book. So 1/3 x minus 5 plus 171 would be the total pages in the book because she finished it. So all of that would equal x because x is the number of pages in the book. So that gives us our final equation right there. 1/3 x minus 5 plus 171 is equal to x, the total number of pages in the book. So to finish up, when you're using symbolic language to represent these word problems, the first step is always going to be defining your variables. You want to start by defining your variable. What is unknown and what are you going to use to stand for that? So, and always state what you want your variable or symbol to represent. Remember that written mathematical statements can be represented by more than one correct symbolic statement. And as you get more experienced in algebra, you will be more aware of when the two seemingly different statements are saying the same thing. And then thirdly, a real help for a lot of these is to break each word problem into smaller parts. So do a section and then go back and see how it fits into the whole part of the statement. Okay, have fun with this. Be sure to just check the answer key as you go along. Give it a good effort and then see how you're doing with them as you go. So if you have any questions, please call.